thanks for inviting me. So this is going to be a talk that's going to be maybe quite a bit more narrow-minded, so to speak, than the previous one, because it's going to be specialized, focused on the computational advances and challenges in planetary dynamo modeling. So I've prepared this with my co-author, Gastine. So it's one of the grand challenges of geophysics to be able to model magnetic field generation in the physical conditions of planetary cores. That's also a computational challenge, and this is why CIG has been invested into that for quite some time now. Among the long-standing questions, we have had models that are necessarily imperfect, but did they produced quite nice results, and but was it for the wrong reasons? So did they get the planetary core force balance right? So even though their answers looked right, was it for the wrong reasons? And do we still need to tackle this challenge of reaching the physical conditions of planetary cores? Or do we better understand what kind of model we need to explain or process a particular kind of observable? So just to put things, to make things clear, this is the set of equations that is solved by numerical dynamo simulation. So here on the left, we have the equation for the flow in the planetary cores, which is basically the balance between inertia, the Coriolis force, pressure, density anomaly, Lorentz force, and viscosity. An advection diffusion equation for the density anomaly. So these are nice visualization from Nathaniel Schaeffer. And the magnetic induction equation that governs the evolution of the magnetic field. The important point to grasp is that there is an important timescale separation in planetary cores. So here I've taken two examples, the Earth and Jupiter, and I introduce you to four important timescales: the magnetic diffusion time, core overturn time, Alfvén time, and planetary rotation period. So these are all representative of key phenomena occurring in those cores, and these are quite very much separated from each other. You can compute three-dimensionless numbers from those four time scales that basically inform you on the magnitude of this time scale separation. So the important ones are the magnetic Reynolds number, that is the ratio of the diffusion time to the overturn time, which reaches about 1,000 in the models, while it's at least 10 to the 5 to 10 to the 6 in Jupiter, and about right for the Earth. The Lundquist number that characterizes the ratio of the diffusion time to the Alfvén time, and the magnetic Ekman number that is the same thing with the rotational time. And you can see that the values are quite extreme. And if we now focus on the Earth's core case, this is the progress that has been done in a decade of numerical geodynamo modeling. So for two of these timescale ratios, and also here I'm talking a little bit about the hydrodynamic Ekman number that involves the viscous time tau nu. There's been not much of an advance, even though we are now closer to Earth's core conditions than we used to be, especially thanks to large eddy simulations that I'm going to talk about a bit later. But the advance still appears for dimensionless number. The magnetic Reynolds number was right 10 years ago, and it still is right. And there's been an advance in the Lundquist number. So the timescale separation of the Earth's core in this case is approached in a bit more realistic way now than before, but we are still not there. So there's been an important effort in undertaken by CIG, and this effort was aiming at comparing the performance of various dynamo codes. So this has been a publication in 2016, a performance benchmark for 15 codes at given accuracy level, where it was concluded that the next generation dynamo modeling will necessarily leverage on approaches of the two-dimensional MPI parallelization type versus 1D MPI plus OpenMP. But on this graph, you can see the comparison of two codes, so MAGIC and Relay. The stampede lines were those of the benchmark in 2016. And Thomas recently recomputed this case of the benchmark with new versions of Relay and MAGIC. And you can see that there has been, so both codes have progressed, but the 1D MPI code in this case, MAGIC, has progressed in a quite a spectacular way owing to the progress of the spherical harmonic transform library SHTNS of Nathanael Scheffer. So this has been a 2.5 time improvement in wall time. So, it's not completely clear whether 2D MPI, it's no longer completely clear whether 2D MPI still will have the edge on a large number of core. So here are a few other data points that can help us to understand where we are going. So here we are basically set a level playing field by using the same code, MAGIC, in 1D MPI and 2D MPI flavors. So you can see these are the latest versions on the same machine. Free run sizes from small to very large. And you can see that MPI 2D scales better, especially on small problems, but is slower. There's an overhead that is intrinsic of this method. And MPI 2D has the edge on max number of radial levels, 1 times 24, so about 10 to the 5, 10 to the 3 to 10 to the 4 cores on this example. So now if I take two MPI 2D codes, MAGIC versus Relay, again, latest versions, again on free run sizes. Here, the difference between those two MPI 2D codes mostly owes to the use of SHTNS, which shows how important it is to use this library in order to perform the spherical harmonic transform on this kind of problem. And now the full graph here has all the codes that we could have access to and make those graphs. So Parody, MAGIC, and XShells, which are free MPI 1D plus OpenMP, and Relay and MAGIC, the same as the previous graph. Again, the latest versions, the same run size. To compare the finite differencing codes with the Chebyshev-based codes, the improved accuracy of spectral codes was taken into account by using half the radial resolutions for those codes of that of finite differencing codes. And you can see that MPI 1D code still, especially XShells by Nathanael Scheffer, still provide the best runtime, the lowest wall time per iteration, thanks to SHTNS and also advanced optimization. But of course, at more than 10 to the 4 cores, you can anticipate that MPI 2D code should have the edge, even though, of course, it's difficult to have access to this kind of resources. So now I'm going to talk about a bit more about the science of this problem. So around in 2010, we had statics and kinematics that looked right in, for instance, this dynamo simulation here, where I plot the radial magnetic field at the core mantle boundary of the Earth versus a geomagnetic field model here, GUFM1. So Uli Christensen did a survey of the accessible parameter space on the left of this slide, and he showed that actually the two ratios of free timescales that I've introduced before could help to pinpoint a region of the parameter space where indeed you had the statics and the kinematics of the dynamo model that looked right. But of course, was it for the wrong reasons was the key question. In the past decade, 2010 to 2020, a number of advanced simulations that I've located here on the same graph have been performed. And of course, the main difficulty is to advance towards the left of the x-axis while maintaining a correct value of the y-axis. That implies an increasing level of hydrodynamic turbulence. So this is the reason why it's more difficult to simulate. So you can see that some simulations on this graph, even though they may be labeled as advanced, they do not appear to advance on this graph because they feature other aspects that are not represented in this subspace and that are advanced. There was another strategy that I have introduced myself with my co-workers, Alex Fournier and Thomas Gastine. The idea was that hydrodynamic turbulence is not important at scale smaller than the magnetic dissipation length scale if you happen to render magnetic turbulence correctly, that is, have a right value of the y-axis on this graph. So this could enable a definition of controlled hyperdiffusive simulations. And there was a companion theory, which was called the path theory, because the simulations draw a path on this parameter space towards the Earth-score condition. And as of today, the path has been explored to 71%, so nearing Earth-score conditions. And the corresponding Ekman number at large scales is 310 to the minus 10. Those large eddy simulations, hyperdiffusive simulations, can also be continued as direct numerical simulation through upsizing, so they can be brought back if you have the numerical resources to direct numerical, fully resolved direct numerical simulations conditions. So how does the solution look like in those advanced direct numerical simulations? So those of Nathaniel Schaeffer are plotted here at an Ekman number of 10 to the minus 7. Azimuthal velocity, density anomaly, and radial magnetic field from left to right. So you can see the scale separation between the large convective scales and the small scales of hydrodynamic turbulence. The magnetic field is not so scale separated because it's very diffusive, so the small scales are diffused away. If you go along this path that I have introduced, you can see this enrichment in small scales of the density anomaly and velocity field, but not of the magnetic field. And you can see that the large scales actually remain very strikingly stable. So that's an important property of this path. If you compare a large eddy simulation and a direct, fully resolved numerical simulation at an advanced path position, you can see also that the large eddy simulation do their job, that is to say, render the large scales of the solution while ignoring the small scales. And all those patterns that I've shown here from various simulations are actually very stable at large scale. So that's an important indication. So concerning the force balance, we have introduced a tool that enables to draw the relative RMS amplitude of force versus the spherical harmonic degree. So it's a scale-dependent representation of the force balance that shows that basically the hierarchy of forces is first a quasi-geostrophic equilibrium between the Coriolis force and pressure gradient, and then a so-called Mach equilibrium between the ageostrophic Coriolis force, so the part of Coriolis force not balanced by the pressure gradient, and the Lorentz and buoyancy force. And then the inertial and viscous force come below. So this is in moderate conditions of the type of those that could be simulated 10 years ago. Now we are rather at these conditions here, and you see that the force balance at the leading order force balance, so at the top of the graph, has not changed much, even though the resolution has increased a lot. But inertia and the viscous force have decreased. And in large eddy simulations, this is the best we can do now, with inertia and the viscous force being pushed even further down on this graph, and first zeroth and first order force balances between Coriolis, pressure, Lorentz, and buoyancy being still the same. So if the force balance doesn't change much as we go to Earth-score conditions, if the spatial structure of the solution at large scale doesn't move much as we go to Earth-score condition, what happens exactly in those solutions. It's in the frequency domain that we find the answer. We find here you have power spectral densities of the output magnetic field of 3 models located at advancing positions along this path. And you see an enrichment in high frequency content as you move towards Earth's core conditions. So this is where the game is now, is in the rendering of the short timescale rapid dynamics of the core. So as an example here, I show an azimuthal acceleration plot of simulated geomagnetic jerks at 71% of the path, where you see both Alven and Rossby waves emerging at the jerk time in this simulation on top of slower dynamics. So this is really those features which are added as you progress towards Earth's core condition, and that cannot be rendered in moderate model. I'm showing it once again here. You see the slow dynamics and then a burst of fast waves, Alven waves to the west and Rossby waves propagating toward the east. This is a representation during this jerk of the Alven waves moving along the field, the slow evolving field lines. So you have a mix of slow dynamics, the field lines and their evolutions, and the short timescale dynamics, the propagation of the Alven waves. So for the Earth, I think we can say now that the right answers have been obtained some time ago for the right reasons, because of this convergence of results from different groups. The link between the earlier models and the present advanced models and the Earth's core is now rationalized. The large scale and the long-term secular dynamics is described by this QG-MAC force balance that I've shown you. It's very stable across the parameter space, and it's also the most likely balance for Earth's core. And on those large scales and long-term dynamics, the turbulence has a secondary role. So if you want to do geodynamics, that is, assess the effects of boundary conditions, physical properties on the long timescales of the geodynamo, the moderate models that we had 10 years ago are basically completely okay. So you can focus on high capacity rather than high performance computing. That is to say, you can compute a large number of cases, of moderate cases, rather than a small number of extreme cases. So viscosity, I think it's been a concern, but I think it's now low enough to be fully irrelevant. And the remaining challenge is the description and explanation of short timescale dynamics, where inertia, even though it's very much smaller than the other forces, comes as a restoring force to generate waves and plays a key role, for instance, in the generation of geomagnetic jerks. So I want to state that other planetary dynamos like Jupiter are intrinsically more complex because of the fact that they have radially spatially variable material properties, and the variations are over a large number of orders of magnitude. And this means that different force balance are obtained at different geographical locations. And this is so the case for Jupiter. And here the challenge remains to be able to really advance direct numerical simulations enough in order to, in the case of Jupiter, capture two interacting layers that feature completely distinct force balance. One where the inertia plays a key role in the upper region, so Coriolis, inertia, Archimedes, and down in the dynamo, in the metallic hydrogen dynamo region, we are closer to an Earth-type MAC balance, or at least we should be. So this is where the challenge lies, being able to interconnect those two regions. And for that, advanced computing capabilities are still needed. Thank you.
Yeah, thank you for this great talk. We do have time for questions. So again, if anyone has questions, you can either type your question in the chat or raise your hand.
Lucy, can I ask my questions? Oops.
Yes, hello, Hiro.
Yep, so thanks for nice talk. So I have a question for the turbulence. So you shown a nice plot for the force balance, but I'm just wondering, so turbulence also make a big effects on heat equation. And so the effect of the turbulence for the heat equation would be appear on buoyancy in force balance. Do you see some change in buoyancy spectrum in your model?
So which kind of model are you referring to here?
In page 18 would be good. Yeah, so yeah, I don't wonder how much buoyancy spectrum could change between your DNS and the LES.
Ah, okay. So this is, I guess this is this slide here. So this is, for instance, a DNS simulation.
Yes.
And here it's fully resolved.
Yeah.
So the buoyancy force has this shape in this kind of simulation. So here, of course, it's a large-scale simulation. So there are, hyperdiffusivity has been applied on the buoyancy force.
Yes, and it's also it also a little bit drops around the radical
Yes.
something like, I guess, no?
So it's normal that it drops because hyperdiffusivity has been applied, but the goal of those large scale simulations is to render the large scales actually of the system. And you can see that up to a spherical harmonic degree of about 80 to 90, you're basically pretty much okay in terms of rendering the force balance.
Yeah. Yeah, so yeah, a little bit what once on how to be, how much we can get a feasible solution for equal 10 between 10 and 20, I guess, ne? Yeah, that's I thought, ne? Thanks.
Okay, so Peter Driscoll has another question.
Yes, thanks for that great talk. And it's nice to see that we're, the force balance is along the path is doing well. My question is sort of along the lines of Uli's, criteria for Earth-like dynamos. Can we talk about whether these, towards the end of the path, towards more Earth-like regime parameters, are we seeing Earth-like magnetic field timescales, like secular variation or even reversals? Some of the longer timescales, I imagine they're just hard numerically to resolve, but do you see a way to actually start testing those sort of magnetic features that we see in the record?
So the time scale of the secular variation is basically tied to the core overturn time. It's usually something like 3 times the core so the time scale of secular variation defined in a standard manner by comparing the power spectra in the spatial domain of the magnetic field and its rate of change. This gives you a key time scale, which is called the time scale of secular variation. And that one ties to the core overturn time. It's usually 3 times the core overturn time. So throughout this parameter space path, this time scale does not change. So it remains, so coming to here, since the magnetic Reynolds number is right, this time scale remains right. So that is not a problem even at the start of the path. This is never a problem. So concerning the reversals now, as you go towards the end of the path, you put your emphasis more and more on the short timescale dynamics, and your numerical simulation will also logically feature a time step that is going to decrease to render this short timescale dynamics, that is going to separate more and more from the slower convective dynamics. So in this situation, you're completely unable, of course, as you go to advanced positions along this path, you're completely unable to simulate timescales long enough to, for instance, observe reversals. So here you have to make the leap of faith, which is to say that models located toward the start of the path are okay to study reversals, and even in an anti-path direction where you would go towards the right on the x-axis of this graph. That's what the community has been doing so far to simulate geomagnetic reversals, and there's been lots of great results that have been obtained through this approach. And the present results, which basically state that the large scales of the simulation do not change, and the convective dynamics does not change, and the dynamics on timescales longer than that of convection does not change either. And I can, for instance, support my comments with, with this graph here, where you see that at low frequencies, it doesn't matter where you are on the path, you get the same signal. So if that is correct, then the leap of faith of using super moderate models to simulate geomagnetic reversals is no longer a leap of faith, it's actually physically grounded.
All right, so I think we have time for one more short question. There's one from John Herland in the chat, which is, if viscosity is no longer relevant, then we can run with homogeneous velocity boundary conditions, v = 0, instead of free slip?
We can run with, sorry, with
homogeneous boundary conditions. I think velocity = 0 instead of free slip boundary conditions. That was the question. It's also in the chat.
So the models I've shown here are run with free slip boundary conditions, but they can be adjusted to no slip boundary conditions. And you can, so v = 0. And then you see that the cost is, of course, a refinement in radio resolution to be able to resolve the boundary layers. But you see that the internals, those boundary layers become so thin that they do not affect the solution in the bulk. So you can basically forget about these and simply set stress-free boundary conditions. So the viscosity at the boundary or in the bulk is fully irrelevant.